Saxon Algebra 2, Lesson 25. Students, greetings. John and I are here today to talk to you about monomial factoring. Wow, that sounds really boring, doesn't it? Sounds like a factory down by the monorail. But it's not. Here's what monomial factoring is. You know how when we distribute, we start with something like this, right? And we turn it into, right? We multiply those and we get something that would look like this, right? If we were just using letters instead of numbers. This is what we call distributing. And when we have this form and we want to go back into that form, we call that factoring. And the monomial part just means John's going to take it easy on us in the beginning and make it not too hard. So what we're doing is we're getting two terms and we have to find what parts of them match. Like in this, it would be the A. And then we're going to pull that out and write it in this format. Okay? So we already know how to do this and now we're practicing that. Ready? Go. Example 25.1. 4ax squared plus 4xy. Okay, so what we look for is the greatest common factor between the two, right? So we start, and this is another place where it's super helpful if we've gone alphabetical. They both have a 4. So our outside factor, what they have in common, we're going to take the 4. What about an A? No. This guy doesn't have an A, so no bueno. What about this x squared? This guy technically has 2 x's, right? Because we could write that like this. Well, this guy's only got 1 back here. So we can pull 1x into our greatest common factor and leave 1 behind. And then I see this guy's got a y, but he doesn't. So 4x is the most that these guys share. So that is going to be like this, right? It's the chunk that they both have in common. So we pull that out and put it on the outside. And then the parts that are left behind are what we'll write inside the parentheses. So if we take 4x out of this one, that means that's gone, but we still have the A. And we took one of the x's, but there'll still be the other one, right? I'm crossing out the 4 and the x that we pulled out here. Okay, so the first term is fixed, and then over here, well, we pulled out the 4 and we pulled out the x, so we're just going to have the y left. That is the answer to this problem. We factored this expression, and you can always test your factoring by distributing and see if you get the original thing back. So if we distributed here, we'd have 4ax squared, check, and we'd have 4xy, check. So we can always complete the circle and come back to the beginning if we so desire. Once you get the hang of these, most students find them easy and fun. 4x squared p squared k minus 6 k squared p to the 4th x. Again, these are a lot easier if we keep them in alphabetical order. We can do it this way, but it just introduces drama. So as I'm copying the problem out of the book, I prefer to get these guys alphabetical. So this one's completely backwards, this one's fine. All right, but we do the same thing. First, we look at the numbers. All right, here they match. That was easier. But here we have to see, okay, what do 4 and 6 have in common? And we quickly see, well, this is, I can write this out, right? I can factor them. Oh, this is 2 times 2. This is 2 times 3. Okay, so we can pull out the 2, right, for our common factor. Then we'll just use this one. X squared, that only has a single x. So we'll take 1x. This has a p squared, and this has p to the 4th. So we can pull out 2 p's, right? 2 p's in a pod. And this one will still have some left. This one we're using up. And then here's a k. This one's got a k squared. So we can pull out 1k, right? This is the greatest common factor of these two terms. All right? I hope That made sense. I wish I could see your faces right now to see if you were going, what? Or, yeah, we get it, it's fine. Now we have to find out what's left when we pull out that part they have in common. So I just go down the list. If I took out 2, right, then I have 2 left. I pulled out 1 x, there were 2 to begin with, so there's still an x. I got all the p's and I got all the k's. Okay, beautiful. Now I go down to the second one. I pulled out the 2, but there's still a 3. I took the x. I took 2 of the p's, but there's 2 more left, right? Because there's 4 there. And then k, I pulled 1 k, but we had 2 of them, so that means there's a k left. Again, a way to check the answer is to distribute and see if you get the same thing back. I'm just gonna check the answer for this one. Yes, yes, yes. The order of the variables within the terms is a little bit different. Like John wrote 3k p squared, but as long as I have all the right letters and the right exponents on the letters, I'm golden. It's good. All right, one more, and then we're gonna change topics. There are 3 topics in this lesson. Cruel and unusual punishment. Not my plan. Ready? 4x squared y minus 2xy plus 10xy squared. I like these problems because you can do a lot of it in your head and there's not a lot of writing and rewriting. All right, I'm gonna double check though, because if I don't copy these right, a lot goes wrong real fast. All right, this one's harder because it's 3 parts, right? So if I want, I can break these numbers down into their prime factors so it's easier for me to see, but I can see that the most I could take out of all 3 of them would be 2, right? Because that's all this guy's got to give. So I'll pull out a 2. And now how about an x, a squared? This is x to the power of 1, right? We can do that if it helps. These guys only have 1, so I can only pull 1x. Y, okay, just 1y, right? Because these guys only have 1. He's got an extra, but sorry. Wait, I didn't mean this. 2xy. There's where my parentheses go. Okay, now what's left? There's a 2 and an x in the first term minus. Remember that when we take all the factors out, that doesn't mean we skip it. That means we have a 1. Right? Because think about when you distribute back, you need to create this middle term. So if we have a 1 there, then this will become minus 2xy, where the 1 is. So the 1 is like a placeholder. And then here we've got 5. Our x is gone, but we've got 1y left. So this is our final answer. This is really tricky. Students struggle over that all the time. You need the placeholder because you can always test yourself. If I distribute, will I get it back? And the 1 allows you to do that. Okay, that's factoring. I remember doing that last year. I always enjoy factoring, you guys. It's fun. Don't you think? All right, the next little section is called cancellation. And it reminds us of a very important rule. There's just one problem. Oh, well, there's 2 parts, the A and B thing. John, that is so lame when you cheat like that. 25.4. Cancel if possible. A, 6x cubed plus x squared over x squared. Now, what everybody wants to say is we can cancel the x squareds. Well, yes and no. Here's the thing. We cannot cancel when we're adding. This addition sign throws a giant monkey wrench into the whole situation. We cannot cancel when there's addition involved or subtraction. We can only cancel when we're multiplying. Only when multiplying. Okay, so that makes us go, oh, are you kidding me? We can't cancel this? Well, we can, but we have to factor first. And I'll show you what I mean. We're going to take the denominator and we're going to factor it, just the way we were factoring a hot minute ago. There's no number here, so we can't pull out a number. We can pull out two x's though, right? Because this has 2 and this has 3. So we can rewrite this as x squared, and then this will be 6 with 1 left over. And then here we have to use 1 as a placeholder, right? Because we pulled everything out. But there's a plus 1. Now, when we write that over this, now this x squared up here is not being added anymore. It's being multiplied against this. So now we can cancel and get 6x plus 1. Okay? So we have to factor before we can cancel. Super important. And students, oh man, it's just so tempting, right? Let's try another one. 6a squared plus x squared over x squared. Now, once again, what everybody wants to do is they want to cancel these, right? And say, oh, well, the answer is 6a squared plus 1. No, we can't. We cannot do that, okay? Because we can't cancel when we're adding. We can only cancel when we're multiplying, and this x squared is being added. So, okay, well, we remember our rule, factor first, right? What can we factor out of the top? Oops, this time, nothing. There's nothing these two terms have in common. So we've reached the end of our rope. And that, no, this was right. I didn't do this. 6x plus 1. This one we can't do anything with. So that is our final answer. Okay? Dun da da da. So you have to factor before you can cancel. All right. Parallel lines. Oh, this C section is about parallel lines. And John's just giving us a little heads up. What he's telling us is, say you have a shape like this, a triangle like this, and we get that little symbol in there. What he's reminding us is that means these are parallel lines, and sometimes it's helpful to extend them and look for transversals, right? Because this angle and this angle will be the same, and this little bitty baby and this little bitty baby, right? You know how this now turns into a transversal? So whenever we see parallel lines in a problem, we can look for transversals. All right. And that will help us prove that the angles are the same, and that will allow us to solve using proportions. Let me show you. There isn't even a problem example for this, but there are problems in the practice set, so what the heck. Let's do 25C from your homework. Look at me helping you with your homework, and it's like I just showed you. We get these little things. This one is 7, this one is Y. Okay, so we're supposed to solve for X and Y. Okay, well, we can do that setting up proportions, right? It would be like this, right? Here's the little triangle, and then here's the bigger triangle. Pretend they're the same. This one is what? 4, 7, and 5. And this one is 4 plus 3, so that's 7 here. And this is 5 plus X, and this is Y. So here's our anchor proportions, and we could set it up to solve for x and y, but first we have to guarantee that these are similar. Because that whole proportion thing won't work unless these triangles are similar. How do we know that they're similar? We have to prove that 2 angles are the same, because if we have 2, then we know that 3 are the same because they have to add up to 180. So how are we going to do that? We know that those are the same because they're peel and stick triangles and they were exactly the same, right? What about one of these other 2? Well, let's just go for this one because we can do it for either way. If we extend this, then we know that these are transversals, right? And this is the smaller, right? Let me do it in the other letter. With transversals, this is the transversal, there's the 2 parallel lines. So this would be the larger and the smaller, the larger and the smaller, the larger and the smaller. And then we can extend this if we want. And the smaller and the larger. So that means this corner's the smaller and this corner's the smaller. Therefore, this is the smaller and this is the smaller. And we know they match. Okay? So the parallel lines allow us to know that a transversal will work, which will allow us to set up these pairs, which will allow us to state that those 2 angles are the same, which means that they're similar triangles, which means we can use proportions. Whew. That's a lot of informing that we got going on there. So the problems aren't any different, but the mental process that we go through to say, yeah, it's okay to set these up as proportions. Are they similar triangles? That's how we can prove it. All right? Much ado about not a lot. All right. I'm excited. We did monomial factoring. Next time, monomial means that they're, what does monomial mean in that context? Let me find out. Oh. The reason we call that monomial factoring is because our answer, what we pulled out, was a monomial. Next time we're going to do trinomial factoring, which is much fancier and fun, and you remember it and you love it. I'll see you in lesson 26 very soon. Goodbye.